Our next speaker, I'd like to invite up James Stasiak, who's a distinguished technologist at Hewlett-Packard, and he'll be presenting on printing the future, building the trillion sensor network, one droplet at a time. Well, it's going to be a hard talk to follow. Trust me, I'm not going to have a whole lot of videos with athletes breaking world records, but hopefully I'll talk about a technology or a convergence of technology which will support the vision that we just heard. So my title is Printing the Future, Building the Trillion Sensor Network, One Droplet at a Time. I work for Hewlett-Packard. One droplet at a time should be pretty obvious. Okay, so what I want to talk to you about today is really an emergence of what's been called the Trillion Sensor Network, and I'll give more details about what the TSN really is, how it evolved, how it intersects the Internet of Everything, the innovation demands and challenges for actually achieving this grand goal. So my thesis or the key message that I'll be trying to make while I'm talking today is that in order to achieve this grand vision of the Trillion Sensor Network, we're not going to be able to do it using conventional technology, nor are we be able to do it with conventional materials. And I want to talk a little bit about the evolution of both, so methods and materials that will help make this grand vision a possibility. And if there's time, I'll spend a little bit of time talking about what I think are pretty interesting emerging methods and materials, such as DNA self-assembly and biological printing. And at the end, I'll give a summary. But we begin by talking about IT, the 5 waves of information technology. It's really sort of the background or backdrop of everything that we're going to be seeing in the next couple of days. So this evolution that started with mainframes and punch cards. How many of you remember punch cards? Okay. Gradually evolving through the personal computing phase, where you had a personal computer sitting on your desk, only connected to the power, not connected to other computers. And finally, the age of the internet, where computers became interconnected, and it was possible to begin to exchange information in ways that we hadn't imagined before. And the evolution of big data, the ability to exchange data and scientific information, really changed the world. Google, I think, changed the world. And then finally, where I see us going, maybe we're already there, is this Trillion Sensor Network. It's really I think the Internet of the future, and the idea there is a completely ubiquitous sensing fabric around the globe, letting us know, giving us time, and time to react, and also time to predict actions and important events around the globe in all state variables. So part of the vision with the Trillion Sensor Network suggests that in the very near future, every person will have 1,000 sensors. And my question is that a reasonable prediction? And just doing some simple math, if we look at the sensors today and where they're deployed, most automobiles have at least 100 different sensors. Smart homes are using tens to hundreds of sensors now. Your smartphone has just a plethora of different types of sensing devices. And we're beginning to see the growth and the adoption of what I would call personal health diagnostics. So the Fitbit on your wrist and other health monitoring devices. So by 2020, 1,000 sensors per person, I don't think that's going to be an unreasonable extrapolation. So I think it's safe to say that the Internet of Things, or the Internet of Everything, is already a part of our daily life, and it's generating a demand for more and different types of sensor technologies and networks. So this demand is beginning to drive and drive to action development and deployment of new sensor systems, new infrastructure supporting those sensors, and new networks. And during the next couple of days, we will definitely see some evidence of the progress of the development of infrastructure and new networks and devices. Hopefully we'll see devices that exhibit ubiquity, so ubiquitous sensors, sensors everywhere, measuring all state variables. I think we're seeing the beginning of contextual and situational awareness in sensors, making them smart in some sense. Sensors that are adaptive, that can react to their environment or react to an event, and in the future, machine learning and other technologies will make it possible for sensors to learn. And I think the other point is, we can look around the room, look around lots of different environments, and we can see sensors everywhere, and sensors that control the lighting in a room and so on. They're not totally obvious, but they're not invisible either. And so I think as sensors proliferate, I think they will become increasingly invisible, and they will blend into the environment in a way that we haven't seen yet. Of course, the other important piece to this evolution, this growth of this new the TSN, is that it's shaping a new global and connected economy that involves small companies that we'll see in the next couple of days, large companies as well. We've already seen how the Internet of Things has affected commerce and shopping. Again, Amazon's probably the best example, but not the only example. There are many competitors that are growing in that space. But where I see major growth occurring will be in the personal health technology space. Not only for fitness monitoring, which I think is growing rapidly, but with an aging population, we would expect more and more technology that allows a person to manage their own health, and when a problem occurs, be able to rapidly communicate with their health provider. Perhaps the biggest customer for the personal health technology space will be your insurance company, who wants to make sure that you're taking your medication as prescribed, the efficacy of the medications that have been prescribed. They want to keep tabs on all of that so that they can build new models new financial models for the future of their companies. Okay, so there's been a lot of sort of visions that have been discussed in the literature. I've picked three. The first is from Stan Williams, a person that I work with on a fairly daily basis. So a few years back, Stan initiated within HP this idea of a central nervous system of the Earth. The idea there was basically what I said at the beginning. Highly intelligent network of billions of nanoscale sensors designed to feel, taste, smell, see, and hear what's going on in the world. So the operative word there is nanoscale, and I'll come back to that a couple of times in the rest of the talk. The other visionaries, so Maya Design, and particularly the authors of this book Trillions, Thriving in the Emerging Information Ecology, Lucas, Bailey, and McManus, they actually put forward and probably coined the phrase the trillion sensor network, and predicted 10 years ago or so that we would begin to see this rapid emergence of sensors everywhere. And finally, I need to recognize Janusz Brzeziak from Fairchild, or he was at Fairchild. So he has spent a lot of time developing what he's called the roadmap for the trillion sensor universe. And if you have a chance to look at any of his literature or his slide sets, he's done a very good job sort of mapping the technology arc, as well as the application arc. So he's done an excellent job. So his comment was, without focused commercialization efforts and availability of standardized development in manufacturing infrastructure, again, operative word here is manufacturing infrastructure, the development and scalability of sensors will be delayed. Just as a tidbit of a fun fact, a trillion sensor market would suggest that you will have one sensor every 10 square feet covering the U.S., or about 150 sensors per person on the planet. And sensor devices, in terms of a business, sort of a business perspective, $76.7 billion by 2017. So it's definitely a market to pay attention to. So the next question is, this ambitious goal of growing this enormous sensor network is, can we afford it? It sounds expensive to try to proliferate trillions of sensors everywhere, measuring all state variables. If you do some simple math based upon the GDP, what you end up calculating, so this was, I have to credit Janusz for doing this little exercise, but what you find out is that in the future, we probably can't afford to pay more than about 10 cents per sensor in order to reach this trillion sensor vision. There's lots of other math that's associated with that, and probably other conclusions that have been drawn. But the bottom line is in order to reach this objective, costs have to be low and continue to drop in the future. I think the next important question is, can we manufacture or deliver the TSN? And my contention, or my thesis is it's not possible, it won't be possible to use conventional wafer-based manufacturing or chip-scale packaging to meet future demands. So two gloomy sort of projections, but really sort of energizing when we begin to think about how we really do deliver the vision. And so what I believe is we need to focus on new scalable manufacturing paradigms that will be required to meet these enormous volumes and continue to drive costs down. Scaling needs to be able to be employed to meet the predicted volumes. And as you'll see throughout the rest of the talk, nanotechnology and nanomaterials and radically different combinations of those are going to become and are becoming necessary enablers. So if we look at what the futurists are saying, I don't know how much importance we place on Drexler or Kurzweil, but they have some thoughts, and actually very supporting thoughts, that nanotechnology and nanobiotechnology will aid and evolve into sort of a different fabric of ubiquitous sensing. So very much wetware meets hardware. Kurzweil continues to drill home the point that we're seeing a blurring of the boundaries between the physical, biological, and digital domains, so much so that when we really harness that capability and begin to really understand the interconnections, we may begin to be able to cheat death. And so it's interesting to read some of Kurzweil's prophecies in The Singularity is Near. And then finally, and probably more technically interesting, the use of DNA as a construction material. So Ned Seaman at NYU has been talking about this for years, but beginning to see biology as a truly functional and programmable material. And so according to Ned, DNA is more than just the secret of life. It's also a versatile component for making nanoscopic structures and devices. Okay, let's take a step back and let's think about where this all began. And arguably you could pick any point, but I'm going to pick Kevin Ashton back in 1999, who was working at the MIT Auto ID Center, and legend or lore suggests that he coined the term Internet of Things during that period. But when he did, it was really within the context of RFID technology and looking at RFID as an enabler and as a way to link objects, not so much for internet communication or ad hoc networks, but to be able to help with things like inventory, smart inventory, how you will be able to connect passive things, say on a manufacturing line, how you verify authentication and security using this new technology. So from that basis, many applications began to grow. So applications in inventory management and asset tracking, logistics, and improved supply chain, all sort of grew out of this first technology. I find it interesting that when I look at where sort of the ice broke for printed electronics, where we saw sort of real applications, it was in the printed RFID space. And so what I'm showing here on the right-hand side is a couple of examples of RFID technology printed on flexible substrates using roll-to-roll methods, except at the bottom right, which is Covio, who made astoundingly good transistors using additive methods. And so RFID, was the first technology to successfully leverage printable electronics. Is it the killer app? Absolutely not. I think we haven't seen the killer app yet. Okay, so I've been talking about digital fabrication and additive manufacturing a bit, and I think it's helpful to provide some definition and some attributes. So when I think of digital fabrication and additive manufacturing, I think about scalability. So scalable manufacturing using scalable methods, and the first one that comes to mind is roll-to-roll processing. Roll-to-roll processing provides a path to low cost, but more importantly, roll-to-roll processing breaks the chain between the fabricator and silicon. And so with the ability to fabricate over large areas, new technologies and new form factors of technologies begin to be possible. Typically, digital methods are maskless, not requiring traditional lithography. Another interesting point is that if you do things right and your material processing is correct, you can begin to use very unconventional substrates, everything from paper to plastic to curved and curved linear surfaces. And so this idea of becoming more and more invisible now becomes easier because you can print sensors in unusual places on unusual substrates and do so at a reasonable cost. So I think the other point that's comforting is that digital fabrication technologies and methods and tooling, they grew from a well-known and well-established technology base, sort of analog printing as being kind of the cornerstone. And so the nice thing about the techniques that are being developed, they often will integrate back with analog methods, but they also, so these digital methods can begin to take advantage of the ability to make different things all at the same time, so variable data and customization. Inkjet methods in particular, I'll talk more about that, are one of the favorite ways of doing printed electronics at this time because of some rather interesting attributes. One is it's sparing in the use of very expensive inks. The last thing you want to do is have a very expensive ink and have to screen print it across or spin and lose 90% of the fluid. And so using inkjet, you can put those materials exactly where you want. Maybe less important, maybe not, but inkjet provides a way to not make contact to the substrate during the deposition process. So if cleanliness or sterility or other factors are important, inkjet methods are a way to achieve that. And finally, with the ability to deposit femtoliters very predictably and reproducibly, you have this ability to have precision dispense. So not only putting a droplet where you want, but putting a very small droplet where you want. And that becomes important as you begin to think about building devices from combinations of printed materials. So as I said, there's a compatibility with older technologies, analog technologies, and just like traditional technologies sort of set the stage for digital technologies, I think digital fabrication and additive manufacturing are providing a great launching pad for 3D printing. And you'll see a lot of that this week, I think. But where I see 3D printing beginning to contribute to the TSN vision, I think and we've sort of already heard the ability to combine, say, electronics and 3D printing, so this emergence of smart objects will become an important player as we begin to populate the Earth with sensors. And finally, I think another area that's very important is the emergence of what I call functional inks. So inks that do more than just put marks on paper, while that's still really a great business. So what I mean by that is inks that can be formulated to have electronic properties or MEMS-like properties, can carry nanomaterials which have very interesting physical properties, and even more interesting perhaps, biological materials. And so we're seeing more and more printed biology, where we're seeing some very fantastic regenerative medicine applications begin to develop. Not so much sensing perhaps, but maybe at some point wetware meets sensing meets hardware. But I think the key messages in all of the digital fabrication sort of vision is that we're not trying to replace silicon, or we're not even looking as an alternative to silicon-based thin film processing. It's a companion process, and I think as we move forward, we'll see more and more hybrid approaches. So if we look back 50 years or so, back into the beginning of the semiconductor days, and we were looking for clues that was going to be an enormous business, I think one of the clues would be companies are beginning to now we're beginning to focus on building special purpose tools that allow you to deposit thin films and do thin film processing. Well, I would say that if we could use that same criteria, that same metric, over the last few years we're seeing lots of companies beginning to develop tools that are focused on digital fabrication and additive manufacturing. Everything from sort of lab scale tools like the Fuji Dynamics printer to pre-manufacturing scale tools. I've listed a few here, but there are many more and probably lots more here this week. All the way to manufacturing scale. And so I mentioned Cativa, and I think Cativa represents a very interesting example. I'll say a little bit more in a minute. And then auxiliary and additional processes and post-processing like the Novacentrix tools. Cativa is interesting because it began with a very simple idea of using inkjet as a way to pattern. It was built on work that was done by Connor Madigan and Vladimir Bolovic at MIT. So this very simple idea of using a novel type of inkjetting has now grown into a fairly healthy company. And maybe there are folks from Cativa here, and if so, congratulations, because I think you've done some very fantastic things, and especially in releasing this manufacturing scale tool called YieldJet. It's here. You can see it. Okay. Printable and programmable materials. I've already talked about the needs for new functional materials, and I won't belabor this, but the development of the ability, the development and ability and capability of printing novel materials is not an easy task. But over the years, people have been very successful at jetting everything from the ancient silver nanoparticles back in the day, all the way out to printed neurons. And so I think we're seeing materials as being a very important player in the growth of this capability. Short list of suppliers. A lot of the folks are in this audience here. I won't belabor that, but what I would say is that there's definitely a growth of companies that are addressing, who recognize the need for novel materials that aid in digital fabrication, largely aimed at building more and more smarter things. And so digital fabrication, I don't know if I need to go through all this, but as I mentioned before, digital fabrication, additive manufacturing also provides a path towards putting intelligence and smart things on all types of surfaces in all dimensions. As I mentioned before, I think 3D printing will take a page and begin to evolve its technology on the back of what we've learned in 2D and 2.5D fabrication. And so if I look at a hierarchy, I won't belabor this either, but if I look at a hierarchy of fabrication methods, there are quite a few. Directed methods like inkjet methods, more interesting, directed self-assembly and evaporation-driven assembly, inorganic and organic chemical templating, biological assembly, as I already talked about DNA, and nano-assembly methods, so the manipulation of individual atoms using tip-based methods. For materials, we're seeing new materials developed every day. So metal nanoparticles began, but where we're ending up, again, is interesting organic and inorganic materials. Companies like Polyera are really innovating in that space. Printable biological materials, shape memory polymers that are printable, and metamaterials that allow us to make fundamental changes to things like the refractive index and dielectric constant of a material. And I think probably I will stop here. I was going to go into some detail about each of these, but perhaps you can stop by and I will talk more about where I see some very interesting technologies developing. What I do want to end up with is saying that the challenge for the proliferation of these sensors is smaller, faster, cheaper, and smarter. And so very much like in many technologies, those are the goals, except for us. I think the needs will begin to leverage nanotechnology, new hybrid technologies, novel materials that perhaps we haven't even invented yet, methods of making nanostructures. All these things I think are going to be combined in order to make this generic, invisible sensor that we can place just about anywhere. Okay, so I'm going to conclude by pretty much saying that I think what we're seeing is a logical continuation of the IT evolution. What I've talked about, so technologies and materials and methods are enabling the trillion sensor network if we can get scale, if we can drive cost. And then looking beyond what I call sort of this digital shoreline, the vision and pursuit of an entirely and pervasively interconnected world is a reality. And it's pushing not only hardware technology that I've talked about, but it's pushing computing, networking, it's pushing basic engineering and physical science into uncharted domains, and it'll continue to bridge hardware, software, and as I've mentioned a couple of times, wetware domains. I think things are going to be very exciting. So with that, I'll end. Thank you.